Hello, Math 223 students. We want in this lecture to talk about distance between different objects in a space. For example, between 2 points, point and line, point and plane, two lines, and these kind of situations. First, let me give this general comment that what we are discussing in this course, we use it in R3, but basically, you can do these methods that I mentioned you can apply them in any dimension Rn. In Rn, we can still talk about a point which has n coordinates. We can talk about one-dimensional line which has a direction and a point, and then it has a parametric equation with one parameter. And we can talk about a hyperplane in Rn, which is basically n minus one-dimensional a flat space, which is defined by one normal vector and a point on it. Still, between hyperplane, one-dimensional line, and point, you can find distances in Rn with the same methods that we discussed. So I'll explain things in R3, and I do examples in R3, but basically you can apply the same computations to Rn in general. Okay, then let's talk about different distance. So first, simplest situation is you have 2 points and you want to find distance between them. As you already know, the distance between 2 points is the same as length of the vector connecting them. So you consider the vector PQ, which connects these 2 points, and then length of that vector is the distance. Very simple situation. And let's do this example. We have these 2 points and we want to find distance between them. So distance is length PQ. Then I compute the vector PQ, which is coordinates of Q minus coordinates of P. It's endpoint minus the start point. So it's 3 minus 1, 4 minus 2, 4 minus 3, which is 2, 2, 1. Then length of this vector, which is root the 2 squared plus 2 squared plus 1 squared, which is root 9, which is 3. So that's the distance between these 2 points in this scenario R3. But it was, if these 2 points were in Rn, you would use the same method to compute the distance. Now let's consider a point and a line. For every other situation, I explained two different methods to do it. Sometimes one method is easier than the other one. For example, in these two methods, method one is easier. But I'll explain both methods. But the example that I do after, I just use the first method to compute it. Okay, we have a point and a line. Let's say line L, point P. One way to compute the distance between this point and line is to consider I explained the method step by step here. Consider a general parametric point on the line. So that's a point which involves one parameter t in it. Then you consider the vector connecting the point and this parametric point. You consider PQT. This is already a vector involving a parameter in its coordinates. Then I ask myself, what is the closest point to P on the line L? That's the condition for being the closest point is that the P connecting P to Q, it's perpendicular to the line. Perpendicular to the line means perpendicular to its direction vector D. So I just write down this condition that PQT dot product with D is 0. That means it's perpendicular to the line. And this is one equation in one unknown T. I solve this equation and find T, and hence I find the location of the closest point on L to P. When I found the closest point on L to P, I just need to compute the distance between P and Q. And I already know how to compute the distance between 2 points. That's one way to do it. Not only will I find the distance between point and line, but I also find the closest point on line to the point. The second way to do it is using orthogonal projection. This time, instead of considering a parametric general point on the line, I consider just one fixed point on the line, completely numeric values. Then I again connect this to the point P, and I consider the vector RP. Of course, R, it's not necessarily closest point to the P, and this is not giving me the distance. But what can I do is I can project down orthogonally to on L. In other words, on the direction of line, which is D. If I project down this vector on the line, okay, that's computation that I know a formula for projection, I can do it. Then basically I get the vector RQ where Q is the closest point to P. Then I have the point R, the fixed point that I started with. I have the vector RQ. Using these, I can find the endpoint Q. And Q is the closest point to the line, on the line to the point P. So then I have the closest point and I can find the distance between PQ to find the distance between point and line. This is the second way to do it. Now let's do one example. I'll do method 1 as practice. You try method 2 and you should get the same answer. Uh, Okay, that's an exercise after the video for you. Okay, let's then compute the distance between this point and this line. As I said, examples that I do are in R3, but basically these methods can be done in Rn in general. In Rn, we have the same concept: orthogonality, dot product, projection. You can do all of these in Rn. And the same computation can be done in Rn to find distance between a point and one-dimensional line in Rn. Okay, so let's go with the first method. So how should I start? Consider the parametric general point on the line. So that is, let's call it QT. It's given by this. It is the point which has x coordinate 1 plus 2t, y coordinate is 3 plus minus t, and z coordinate is negative 2 plus t. This is a general point on the line. Then I consider point P connected to this PQT. Okay, PQT. But then I apply the condition that PQT should be orthogonal to the line. In other words, dot product with D should be 0. What is the direction vector of this line? This is direction vector of this line, this vector. So I write down dot product with D should be 0. Then let me compute this. PQT, it's this minus this. Coordinates of this minus coordinates of this. Which is 1 plus 2t minus 3 becomes negative 2 plus 2t. This minus 1, which is 2 minus t. Then this minus 4, which becomes negative 6 plus t. Then dot product with D. D is this. 2, negative 1, 1, negative 1, 1, it should be 0. Now, this times this, it's negative 4 plus 4t. This times this, it's negative 2 plus t. And this times this, it's negative 6 plus t. So adding the constants, negative 4, negative 2, negative 6, you get negative 12. Adding t terms, it's 1, 1, and 4 the coefficients, so in total 60. So this implies that this is 0, so 6t equals 12 or t equals 2. I found the location of the closest point on the line to P. So the closest point is, let's call it Q, is, this is the general point. For t equals 2, the parameter 2, I get the closest point. I put 2 in this, and I get 1 plus 2 times 2, which is 5. 3 minus 2, which is 1, and the negative 2 plus 2, which is 0. This is the closest point on line to this point. Now the distance between P and L, it's the same as distance between P and this closest point. So I compute PQ, length of it. And this will be the distance that I'm looking for. Okay, PQ, what is it? It's Q minus P, that's 5 minus 3, 2, 1 minus 1, 0, 0 minus 4, negative 4. And then length of this vector, it's 4 plus 0 plus negative 4 squared, 16, which is root 20 or 2 root 5. That's the distance from the point and the line. Not only I found the distance, I found the closest point on the line. Again, as exercise, do method 2. You should get the same closest point and the same distance. Okay, now the next situation, point and plane. We discussed this in the lecture, but let's quickly review it. One method is to consider the line that passes through the point and it's perpendicular to the plane. In other words, the line that have this point and the direction of it is the normal vector of the plane. So consider this line, write down the equation of it. Then intersect this line with the plane to find the closest point, Q, closest point on plane to the point P. Now that you have the closest point, find the distance between P and Q. That's one method. Another method, again, use orthogonal projection. Instead of considering the line, consider just one fixed point on the plane, not necessarily the closest point. Then I connect this point to this point P, and I have this vector, which is not necessarily giving me the distance because it's not, R is not the closest point. But again, I use projection to get what I want. This time I project it in this direction. I project it down into the direction of N, normal vector. And what I get is this vector. This vector QP, where Q is the closest point. Now that I have the vector QP, length of it give me the distance. And if I want to find the closest point on the plane to point P, then I can also do that because I have the vector QP by the projection I found it. And also I have one endpoint P. I can find the other endpoint Q, which is the closest point on the plane to the point P. Okay, let's do an example. Again, I just do method 1 and do as an exercise method 2 and see that you get the same answers as mine. Okay, we have again for the, I think, third time, this complete computation, everything, method 1 and method 2 can be done in Rn. But in Rn, the plane is a hyperplane. That means it's a n minus in Rn, the plane or hyperplane, it's n minus one dimensional object, flat space, which has one n as normal vector and 1 point. And then the equation of it, it's similar to the equation of the 2D plane in R3. And you can use the same scenario as here to find the distance. Orthogonal projection, orthogonality, dot product, all these operations exist in Rn as well. Okay, we have this point and this plane. What is the distance between this point and this plane? If I want to go with method 1, first I write down the equation of the line pass through P with the direction normal vector. What is the normal vector? It's the coefficients of x, y, z. So the normal vector is 2, 1, negative 2. Hence, the equation of the line, let's call it L, passing through P, and perpendicular to the plane, it's given by x, y, z equals equation, the points on the line in the vector form, so negative 1, 3, negative 2, plus a parameter and the direction of the line. The direction of the line, it's the same as normal direction, normal vector of the plane, which is 2, 1, negative 2. And t, it's a general real number, a parameter. This is the equation of the line. Then I need to intersect this line with the plane to find the closest point Q. So intersection of L and the plane. This is the equation of the plane and this is the equation of the line. So the easiest way to intersect these two is to read x and put it as x here. The same for y, read it as here and put it here, and the same for z. Then you get one equation, only one variable t, and you find t. So let me do that. It's 2x, but x on the line is this, negative 1 plus 2t, plus y. But y on the line is this, 3 plus t. Then minus 2z, minus 2z. Z on the line is this, negative 2 minus 2t. And this should equal negative 13. Equal negative 13. This is the one equation, one unknown that I can easily solve for t. Let me expand these. I get negative 2 plus 4t plus 3 plus t minus minus plus 4 and minus minus plus 4t. If I add the numbers, negative 2, 3, 4, 7 minus 2, 5. And if I add t terms, that's 4 plus 4 plus 1, 90. Then I move 5 to the other side, negative 13. You get 90 equals negative 13 minus 5, which is negative 18. Divide 9, you get t equals negative 2. Now that I have t, I found the intersection point or the closest point on the plane to the point. I put t here and I find the x, y, z coordinate of the closest point. So the closest point, let's call it Q, is putting this in this equation. So negative 1 plus t, which is minus 2 times 2, which is plus 4, basically. No, minus 2 times 2, minus 4. 3 minus 2 times 1, which is minus 1. Minus 2. Minus 2. And then minus 2 times minus 2, which is plus 4. So the closest point is negative 5, 1, and 2. Now that I have the closest point, I find the distance between 2 points, P and Q. And that's the distance between point and the plane. So the distance that I'm looking for, it's PQ, length of it. PQ, it's this point minus this point, which is negative 5 plus 1, negative 4, 1 minus 3, negative 2, and 2 minus minus 2, which is 4. Then length is root of negative 4 squared, 16. Negative 2 squared, 4. 4 squared, 16. 16 plus 4, 20 plus 16, it's 36. Root 36 is 6. So the distance is 6. And this is the closest point. Not only I found distance, I also found what point on the plane is the closest to P. Okay, now we consider any combination of point with something else, like point, 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 line, point, plane. Now I want to consider line, 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 point, line, plane, 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 and these kind of things. But first, let's discuss this remark that if you have two parallel objects, let's say two parallel lines, or two parallel planes, or one line and one plane, but still parallel. If this is the situation, basically the distance is the same as distance of one arbitrary point on one of the objects to the other object. So basically it reduces to the previous situation, distance of a point and another object. For example, you have a plane and a line that are parallel. You take just one arbitrary point on the line and then just ignore the line. As long as they are parallel, the distance is the same as distance of point and plane, this point and this plane. So because of this, basically, I don't need to discuss the distance between parallel objects because they reduce to the previous situation, distance of a point and a line or a plane. What about if they are not parallel? Then either they intersect or they don't intersect. If they intersect, distance between two intersecting objects, like two intersecting line, two intersecting plane, it's simply 0 because they intersect. So then we remain with the situation that two things are not parallel, but they don't intersect as well. You cannot have two planes or even in Rn hyperplanes that are not parallel, but they don't intersect. Any two hyperplane or plane in R3 that are not parallel, they intersect. And also you cannot have the situation for a line and a plane or line and a hyperplane in Rn. If they are not parallel, they intersect. So basically there is no situation, no new situation between two planes or line and plane. But between two lines, you can have the situation that they are not parallel, but also not intersecting. If you remember, this is called, this situation is called skew lines. You have two lines, like if I have another, like let's say this, my finger and this line, which is a pen. These two lines are not parallel, but they don't intersect as well. This situation, skew lines, I need to discuss the distance between these two situations. So again, I consider two methods. One of them is much faster and easier than the other one, but it has some drawbacks. I will mention its drawbacks after I discuss it. So what is the easier method to find the distance between two school lines in R3 or Rn? That one of the drawback is exactly that method one can only be done in R3. In Rn, method one, it's not available for you. I will discuss it after. But let's discuss the method first. So you consider one fixed point on each line. One fixed point on L1, one fixed point on L2. Not parametric general point, just one fixed point. Then you connect them, you get PQ. These two are not necessarily the closest points. So PQ does not give you the distance. But again, you can project in some direction to get the distance. But what direction? The direction that you should project is a direction that is perpendicular to both lines. Since it should be perpendicular to both lines, it should be perpendicular to both direction vectors. And as you see this week, the mechanism that give you a direction that is perpendicular to two given vector, it's cross product. So basically, cross product of direction D1 and D2 give you a direction. And you project this into that direction. And then length of this projection give you the distance. That's as simple as this. So we do take one fixed points, then this is the distance. PQ projected in the direction of cross product of the direction of two lines. And length of this vector. This is the distance. Now let's discuss what is the weak point or drawback of this method. One, it cannot be done in Rn. Because cross product, it's an operation that you don't have it in Rn in general. You have it in R3, but not Rn in general. Dot product, you have it in Rn, but not cross product. Second drawback, I found the distance, but what are the closest points? I don't know. I cannot find it by this method. If I also want to find what are the 2 points on these lines that are closest to each other, this method doesn't give that to you, only give the distance. So if you are in Rn, or if you want also the closest point to each other, then you should use method 2, which is a little bit computationally, conceptually it's even easier, but computationally usually it's slower than method 1. What is the method 2? Consider two parametric point on the lines, not fixed points. 2 points that involve parameter, basically general points. General point on L1, general point on L2. Let's call the parameter on L1 S, parameter on L2 T. So you have QTPS. Then consider the vector connecting these, and again ask the same idea as here, line and point. I would ask myself, what is the situation that this is the closest point? It's the situation that it's perpendicular to the line. So again, these 2 points are the closest point to each other if this vector PSQT, it's perpendicular not only to L1 but to both lines, L1 and L2. Write down this equation. PSQT, it's perpendicular to line 1. In other words, dot product with D1 is 0. PSQT, it's perpendicular to line 2. In other words, dot product with D2 is 0. This is a system of equation. 2 equations and 2 unknowns, S and T. You solve this system of equation for 2 unknowns, S and T. Then when you found S and T, basically you found one location, one point on L1 and one point on L2, which are the closest point to each other. So now you have the 2 closest points. And the distance between these 2 closest points, it's the distance between the 2 lines. This method can be done again in Rn and also give you the 2 points that are closest to each other on the lines. But it's slower than the method 1. Now let's do one example. I do the faster method, method 1. You try to do method 2 and see that you get the same answer. So since I'm using method 1, I cannot find the closest point. I want just find the distance. That's it. Okay. How would I do that? Take one point on each line, fixed point, not parametric point. So one point on first line is this. Let's call this P, the point version of this. This is a vector, but let's call the point version of this P. And the point on second line, let's call it Q. Now I need also directions of the lines. And then I need to do cross product of them. So direction of the first line is this. The direction of the second line is this. Now I need the direction which is perpendicular to both lines. In other words, which is perpendicular to both D1 and D2. What is the vector which is perpendicular to both D1 and D2? It's the cross product of them. So I compute the cross product of this. It's determinant I, J, K, D1, which is 1, 2, 3, D2, which is 1, 0, 2. Then I expand according to the first column. I get I, then removing this determinant, which is just 2 minus 2 times 2, 4 minus 0. So it's 4i, then minus, minus j, and removing this, then this determinant, which is 2 minus 3. 2 minus 3 plus k, and then what determinant? Removing this, you get this determinant, which is 0 minus 2, which is minus 2. So the vector that I want is this vector. For negative, negative 1, which is 1, and negative 2. Okay, good. Now, I also want PQ, and then I need to project this onto that. So PQ, what is it? It's coordinates of Q minus coordinates of P, which is 0 minus 2, 1 minus minus 1, which is 2, and then 3 minus 1, which is 2. Then I need to project this onto this. Project the distance that I want to compute is projecting PQ onto this, which is D1 cross D2. When I do project this into this direction, I get the vector which its length is the minimum distance. So length of this. Now let me do the computation. The formula for projection, let me recall it. It is projection of, let's say, V on W, just the formula. It's V dot W, length W squared, and then W. This is the formula for orthogonal projection. Let me use it. Dot product of these two vectors. In other words, dot product of these two vectors, which is 4 times negative 2, negative 8, 2 times 1, 2, 2 times negative 2, negative 4, over length of this vector. This vector is this one. So length of that squared. So 4 squared, 16. 1 squared, 1, negative 2 squared, 4. This is root length and then squared. So they cancel each other. It's just this. And then the other vector, which is D1 cross D2. So this vector, I need to copy it here. 4, 1, negative 2. Okay, good. Now I compute the length. So first simplifying this, you get negative 10. Simplifying this, you get 21. And now consider length of this. When you compute, or let me first write it and then distribute the length. Okay, then length of this. For the number one, for the scalar that I have, I need to take absolute values to get absolute value negative 10 over 21 and length of this. But length of that is root 4 squared plus 1 squared negative 2 squared. It's basically what I had computed before. It's this which I computed as 21. So this is root 21. Length of this vector, it's root 21. What I have here, it's basically a square of root 21. Then you simplify root 21 and 21, and you drop negative sign by absolute value. You get 10 over root 21. And this is the distance between these two lines. Okay, that's all I wanted to discuss for this video, and I hope that it was helpful. Thank you for watching.